In this video, I'm going to talk about relativistic kinetic energy. This is the formula for kinetic energy that's commonly presented in physics courses. Here, I'm using K to represent kinetic energy, gamma to represent the Lorentz factor, m to represent mass, or rest mass if you prefer that term, and c to represent the speed of light. This is an equivalent formula for relativistic kinetic energy, and in this video, I will derive it and discuss the advantages it has over the standard formula. First, let's talk about the main issue with the standard formula for kinetic energy. While this formula is 100% valid, it needs to reduce down to the classical expression for kinetic energy. And for most of us, it's not immediately obvious how to do so. Probably the most common way to show that this formula here is going to reduce down to the classical form, 1/2 mv squared, is to use the binomial theorem. So I'm not going to go through and show the whole binomial theorem and talk about that. I'm just going to focus on one consequence of it. Specifically, if the absolute value of x is much less than 1, then the quantity of 1 plus x raised to the n power is approximately equal to 1 plus nx. Now you may be wondering, what do I mean by much less than? Essentially, I mean small enough so that this approximation here is valid. Usually that's at least a factor of 10, so you're talking about 0.1, but usually it's even smaller than that. Now let's look at gamma, which is 1 minus v squared over c squared, that entire quantity raised to the negative 1/2 power. So if v squared over c squared is much less than 1, then we're going to let x equal negative v squared over c squared and n equal negative 1/2. Okay? And so gamma is going to be approximately equal to 1 plus v squared over 2c squared. So returning to our original formula for kinetic energy, we can make use of our new expression for gamma. And what we're going to do is we're going to substitute this in for gamma right here. And now you could see we've got this 1 and this negative 1. So when we add those together, those are going to cancel. We're just going to be left with this term here. And notice these c squareds are going to cancel. And so consequently, we're just going to get the classical form for the kinetic energy, just 1/2 mv squared. So the point being, in order to show that this formula, that the kinetic energy, the relativistic kinetic energy, becomes the classical form, we have to use the binomial theorem. It's not at all obvious that this would happen otherwise. Now I want to go through and derive that alternate expression, that equivalent expression for the relativistic kinetic energy. So we'll go back, we'll start here with our original equation for relativistic kinetic energy, but we're just going to focus on gamma minus 1. So specifically here, we're going to multiply both the top and bottom by gamma plus 1. And now if we multiply these expressions in the numerator together, we get gamma squared minus 1. Now I'm going to take this next step, which isn't necessary, but it does make the subsequent math steps a little easier to follow, I believe. So I'm going to factor out the gamma squared. That's all I did here. And you can see if I multiply gamma squared back through here, I'm going to get this expression. Gamma squared times 1 is just gamma squared. Gamma squared times 1 over gamma squared is just 1. Okay. So I just factored this out. And now I'm going to take another step that, again, is not at all obvious. I am doing this one specifically because I think it makes the subsequent steps a little easier to see. What I'm going to do is, instead of leaving it as 1 minus, I'm going to change it to 1 plus negative 1 over gamma squared. And you'll see why in just a moment, but now let's focus on gamma. Remember that gamma is just 1 over the square root of 1 minus v squared over c squared. Okay. So now we're going to do gamma squared. That gets rid of the square root. Now we're going to take the reciprocal of both sides. So now we've done the reciprocal of both sides. And now the last step, we're going to do the negative of both sides. So we're going to put a -1 here, and then this becomes -1, and this becomes plus. And what we're going to do now is substitute that in. You can see I've highlighted here, this term has now become this term. And now you can see we've got this 1 plus -1. So of course that's going to cancel, and we're left with this expression. So we've shown that gamma minus 1 equals all this. So going back to our original formula for kinetic energy, we have gamma minus 1 here. We're going to substitute all this in. So you can see I substituted all this in for gamma minus 1. And now notice these c squareds are going to cancel. And we're left with the expression. This is our equivalent expression for the relativistic kinetic energy. It's fine to express it this way. I prefer to express it this way. To the best of my knowledge, this formula was first published or presented by Wendell Holliday back in 1987. He published this in the American Journal of Physics. And right here you can see the formula. Notice that he, instead of using m, he's choosing to use m naught. That's how he chose to represent the rest mass. Now I like this formula because I think it makes it a lot easier to see how we go from the relativistic formula to the classical form. If v is much less than c, we know gamma is approximately equal to 1. 1 squared is 1. 1 plus 1 is 2. And so we quickly get the classical form 1/2 mv squared. In my mind, that's a lot easier, a lot more straightforward than going through the binomial theorem. Additionally, we can also look at the formula for relativistic momentum, P equals gamma mv. We can substitute that in here. And if you do that, you get P squared over the quantity of gamma plus 1 times m. Well, if gamma is approximately equal to 1, then we're going to get 1 plus 1 down here. That's going to be 2. We're going to get P squared over 2m. And again, this is the classical form. It is quite common to express kinetic energy, the classical kinetic energy, as P squared over 2m. And so we can see where that comes from. Now there's one more thing I want to show you. I have not found this anywhere else, but if we let gamma equal the golden ratio, so I'm using phi to represent the golden ratio. If you don't know what the golden ratio is, look it up. It's very important math. It seems to show up a lot in nature. To calculate it, you just do the square root of 5 plus 1, and then you divide that whole thing by 2. It comes out to approximately 1.618. It's actually an irrational number, so there's a whole bunch more digits, but approximately 1.618. And if you stick that in here, this whole fraction just becomes 1. And so we're just left with k equals mv squared. So in that specific case, which of course happens at a very specific speed, that speed is something like 0.786 times the speed of light. But at that speed, the kinetic energy is just the mass times the square of the speed. I thought that was pretty neat, something unusual that happens specifically when the Lorentz factor equals the golden ratio.